Welcome to another pumping example. So in this example, water is being pumped out of a pool, which is 30 feet wide and 50 feet long. The depth of the water varies as shown in the cross section below. So the water is pumped another 1 foot above the top of the water. If the water weighs 62.4 pounds per cubic foot, how much work is performed in emptying the pool? So I'm just going to slightly add to this diagram. So in addition to this, we have our 30 feet width, right? We have 50 feet long, and then of course the depth changes depending where we are in the pool. So we are pumping water out of this pool an additional 1 foot beyond the top of the pool. And we are going to pull the same trick that we pulled in the last video. So we are looking at slivers of water. So these slivers of water have width dy. Whoops. Did not mean to erase all of that. So these slivers of water have width dy. And we are raising these slivers of water out. So I'm gonna, by some distance. So what I'm gonna do here is this time around, I'm gonna put my 0 at the top of the pool. So this will be my 0. Y will be simply the distance from the top of the pool downward to the layer of water. Note that Y will be negative going down here. The top of the spigot is therefore at 1. The bottom of the pool is at -10. So our Y values will be negative here. We are raising this water out of the pool. And so the volume of our sliver, or the volume of our layer, is going to depend on where we are in the pool, right? So it depends on the depth. So for Y between -4 So for Y between -4 and 0, we have the entire width and length of the pool. So for 0, or for -4, less than or equal to Y, less than or equal to 0, the volume is just the 50 feet long times the 30 feet wide times dy feet, or 1,500 dy cubic feet. And so if we're in the top portion, our length is just that constant 50, the width is that constant 30, and the height of the layer is just dy. On the other hand, for -10, less than or equal to Y, less than -4, we can actually do less than or equal to. The volume is a little more complicated. So if we draw our picture, so here's our y. It's a negative value. The distance here would be 10 plus y. That's y minus a negative 10, since negative 10 is the bottom value, otherwise known as 10 plus y or y plus 10. Actually, that y is probably going to go farther. So let's do this first. So we have negative 10, and then at the top here is negative 4. We have the bottom here is length 15 feet. And then the entire length was 50 feet. We have 15 feet at that bottom and then 10 feet flat on the side. Leaves us with this length must be 50 minus 10 minus 15, otherwise known as 25 feet. So if we take a sliver here, we want to know essentially how long that sliver is. And so we're going to break it up into two pieces. So we know that we have the 15 feet component. And we need to know what the missing part is. Once again, we can pull similar triangles. So if I pull similar triangles, my large triangle is 25 feet and 6 feet tall. My small triangle is this here is essentially negative y in length, going from 0 down to y. The whole thing is 10 deep in length. So we would do 10 minus negative y, or 10 plus y, as I'd mentioned before. So we have our similar triangles. Again, we have our large triangle that is 6 feet tall and 25 feet wide, versus our small triangle that is 10 plus y versus our unknown. So that we have the unknown is to 25 as 10 plus y is to 6. That means that our unknown is therefore 25/6 times 10 plus y. So we have 15 feet and 25/6 times 10 plus y. You also could have figured out what the missing distance was to get us all the way up to 50 and simply subtracted it off. That's a perfectly acceptable route as well. So our layer, we have height dy, length of 15 plus 25/6 times 10 plus y. And then our width is 30. So this means that the volume should be 15 plus 25/6 times 10 plus y. That whole thing times 30, and then times dy. This is the same thing as, let's see, 30 times 15, we would be looking at 450. Plus, if we do 30 times 25/6, that would be 125 times 10 plus y. This whole thing times dy. Or we would have 450 plus 1,250 would be 1,700 plus 125y, all multiplied by dy. So this is for -10 less than or equal to y less than or equal to -4. So we can just check at -4, we would have 1,700 plus 125 times -4. So that would be 1,700 minus 500 or 1,200. Which does not seem quite right. One moment. Never mind. It is fine. So this would be for less than, so we don't have conflict. We go from -10 less than or equal to y to less than -4. At -4, we suddenly add another 300 times dy due to that sudden jump in volume, so that, or in length. So that does give us what we were looking for here in terms of volume. So here we have our two pieces for volume. So essentially we have our volume of layer. So our volume of a layer is, we had 1,500 times dy for -4 less than or equal to y less than 0. And we had 1,700 plus 125y times dy for -10 less than or equal to y less than -4. From here, we need to calculate the weight. So the weight of a layer we are working in the imperial system. So the weight is just volume times our weight per cubic foot. So we were 62.4 pounds per cubic foot. So we do our volume times 62.4 pounds per cubic foot. So this is, we would have 1,500 times 62.4 dy, where -4 less than or equal to y less than 0. And we have 1700 plus 125y times 62.4 dy, or -10 less than or equal to y less than -4. So this is our force. Required to move that one layer wherever it's at. Right? Then for the distance, each layer must move -y feet, right? Again, y is a negative number, so the distance would be -y to the top of the pool or the top of the tank, plus 1 foot extra, 1 foot above the tank. So the distance would be 1 minus y. From here, we get the work required to move one layer. So the work required to move a layer is given by, we take the force multiplied by the distance. And so in this case, we have our two separate pieces. So we had the first component was 1500 times 62.4, which if we multiply that out, we're looking at 93,600 times our distance of 1 minus y, and then dy. For the second component, we have 1700 times 62.4 is 106,080. Then to that, we add on 125y, 125 times 62.4. Which is 7,800 times y. Multiply that by 1 minus y, then times dy. So the first component was for -4 less than or equal to y less than or equal to 0. Our second component is for -10 less than or equal to y less than -4. So at this point, now we have our work. Now we just have to sum up all of the work. So I'm going to do this in two integrals. I will do one integral going from -10 to -4. So that will be our 106,080 plus 7,800 y times 1 minus y dy. That takes care of all of the layers between depth of 10 and 4. And then to that, we need to add the integral from -4 to 0 of 93,600 times 1 minus y dy. I'm going to stop at this point you certainly are fully capable of evaluating these integrals. So I will stop here. And let you finish evaluating the intervals. But again, the general idea here was the same as in the previous video, where essentially we were calculating, okay, what is the total volume at each layer? And then finding its weight, and then multiplying by that distance that that particular layer had to travel. Once we do that, add them all up. That's just in this particular problem. The formula for the volume had two sort of distinct components. And so we had to find our two separate components. You'll notice both in this problem and the previous problem, similar triangles came in handy. The other thing you could have done would be essentially to write an equation for the line that is on the slant is also a possibility. I tend to like to work with similar triangles. But this is how we can go about calculating work when we're pumping water out of a pool that has sort of a varying lengths depending on the depth.